Hello, everybody, and welcome to our webinar. My name is Ronald Paredes, and I'm a Senior Applications Engineer with OutBack Power. The purpose of this webinar is to present, it's twofold. Number one, to present a brief introduction to those who are new to solar, and also to transition those who have been doing grid-tie systems and want to transition into battery-based systems. The topics that we're going to talk about are things like off-grid systems, grid-tie but battery backup systems, grid-tie and grid interactive systems, and AC coupling applications, which are becoming more and more prevalent in this industry. The contacts are going to be, I'm going to display these contacts at the end of the webinar as well, so no need to rush and copying them right now. So we're going to go into some applications of grid standalone, which are basically the same thing, grid backup, grid support, and grid hybrid, grid interactive applications, meaning when you inject energy into the grid, and AC coupling applications. Here's a picture of a standalone or off-grid application. We have the PV array, we have our renewables here going through a charge controller, and the purpose of the charge controller is to do the charging of the batteries in a controlled way. The charge controller will basically control the current and the voltage, and this is all completely programmable, and that will then go onto the batteries, and then the batteries, although it doesn't really show here, is the central node for the output of the charge controller and the inverter. So here we have two inverters for a 240-volt system. Each inverter provides one phase. If this was just a 120-volt system, we would only have one inverter for the 120 volts. But basically here, the one thing that I want you to notice is that there is no grid. We have basically three sources. We have our two renewables, the sun, the PV modules, and the wind turbine, and an AC generator. Our inverters have the ability not only to invert from DC to AC, but also to charge the batteries from an AC source. The other three components that are very important to note here are the programming unit that we call the mate. We have three different versions, mate 1, mate 2, mate 3, with mate 3 being the latest and most flexible one and the most powerful one. The hub allows communication between the programming unit and all the rest of the devices here. And then the FNDC, which we'll get into more, is basically a battery/system management tool. Here's a grid-connected system. This is, although it's grid-connected, it's acting only as a backup system. So here, the inverter, when the grid is normal, the inverter is basically a wire. It allows the energy to flow through the inverter and right onto the loads. When the grid fails, the inverter will notice that and will automatically export power from the batteries and begin to back up the protected loads. The one thing that's very important to note here as we're talking to customers and describing this to people is that you don't want to back up the entire system. You really only want to back up the essential loads. And the reason being that the bigger the system that you want to back up, the more the loads and the longer the running time, the bigger the battery bank is going to have to be. One of the things that I've seen with over time is that people will initially want to back up the entire home, but once you describe to them how much energy they'll be consuming if they really do want to back up the entire home, then that battery bank can go from a few batteries to a battery room. So very, very important to keep that in mind. But just want to reemphasize again here that the inverter will automatically transfer from the batteries once it sees the grid fail. And that transfer time is completely programmable. You can tell the inverter to do it within 0 cycles or 240 cycles, which in a 60 hertz line, it basically means from 0 to 4 seconds, and that's completely programmable. Here's a another system that's basically a backup system, but it has two other components. It has our PV modules and the charge controller. And also, please note here that the yellow arrows here are basically they're flowing in one direction. They're flowing from the grid, through the meter, through the service entrance panel, through the inverter, and onto the protected loads panel. The PV modules here are sized. They can be sized to serve the protected loads or to increase the autonomy of the system. So, but the main thing here is that the inverter here is also just a wire, and should the grid fail, then the inverter will then switch back to the batteries, and it will begin exporting power from the batteries to the loads. So here essentially we have two sources. We have the PV modules and we have the grid. This is again to point out and to reemphasize that it's critical that people really only power the essential loads. For example, an example of a load that you would not want to back up is an air conditioning unit, because it draws tremendous amount of power, and it would require a very large battery bank to really provide the energy that it's going to be consuming throughout the day or throughout the period where the grid goes out. Here we have essentially three sources. Here we have the grid that powers the entire system under normal conditions. We have a backup generator, and we have PV modules. And please note that there is a transfer switch here. Now, the reason this transfer switch is there is because our smaller FX inverters can only take one AC input. So here we can either have the grid feeding the inverter or a generator going into the inverters, and we have to go through a transfer switch to essentially choose which AC source we want to use to power the loads or to charge the batteries. And here at the bottom here we have our PV modules feeding our charge controller. The charge controller then is doing the charging of the batteries, and if the batteries in this case are fully charged, then they will then essentially the current that's being harvested will essentially be going into the inverter and onto the loads. So here we have two situations. If the batteries are fully charged, everything that's being harvested will basically be going to the loads. And if the grid fails, the inverter then switches from the grid to the batteries. And if the failure happens at night, then we have the batteries as a source. And if it happens during the day, then we have both the PV modules and the batteries. Here's our grid interactive system, which basically injects power into the grid. So please note that, let me go back here. Please note that here the arrows are flowing from the grid and onto the system in one direction only. And here the arrows are they're going both ways. So the system has the ability to inject energy into the grid. So our PV modules will essentially, the energy that the PV modules are harvesting will basically go to the grid if the batteries are fully charged, and if the loads are minimal, or if we have no loads, they will then go to that excess energy will then go into the grid. We have different models that are designed for this type of function, and essentially what they look for is a stable grid in terms of voltage and in terms of frequency, which we'll get into a bit later. But basically we have modules that are designed for standalone, off-grid, and backup systems, and then we have models that are specific to grid interactive applications. Essentially, you can use the same model for off-grid or standalone, and for backup, since you're not injecting energy into the grid. These are the windows. This window is in our manual. I just want to point out that essentially the failback voltage is 108 to 132, and the AC frequency needs to be between 59.3 hertz to 60.5 hertz. So these are the windows, the voltage and frequency windows that the inverter will look for before it injects energy into the grid. Initially, a lot of the solar systems that were being installed were basically just a grid-tie system, a battery-less system with no backup, where you only had your PV array, your grid-tie inverter, and then basically that went onto the grid. But the problem, again, remember our table here, is that the inverters for UL 1741 are fixated basically on looking for these voltages and these frequencies. And so if the grid goes out, even if the failure happens during the day, once the grid goes out and we have a voltage and frequency, basically they deviate, or they have an excursion in voltage or frequency away from these two windows, the inverter has to stop injecting power into the grid or into the system. And so a lot of people realize that even though they have a PV array and even though they have an inverter, because the inverter is programmed to follow the UL 1741 windows and the IEEE 1547 guidelines, they stop injecting energy. So essentially they are without backup just like everybody else. And so a way to add backup to a system that didn't have batteries is to couple a battery-less inverter with a battery-based inverter on the AC side. So this AC coupling system essentially allows the system an existing system to have backup when the grid goes out. And essentially the sequence is that when the grid goes out, our inverter here will notice that, because that's what it's programmed to do. Will notice that the grid went out. It will then start exporting power from the batteries, and it'll export a nice pure, nice sine wave signal that is going to be 120 volts and 60 hertz. It will then display that basically on the critical loads panel. The battery-less inverter will then notice that it has a 120 volt, 60 hertz signal, and after a 5-minute wait period, it will begin. If this is during the day, it'll allow the whatever energy is being harvested from the PV array to flow onto the loads if this is during the day. And if the failure happens at night, then the batteries will be supplying, essentially will be supplying the power to the system. Here is a block diagram that shows how basically the energy flows. Here's our PV array. Here is our battery-less inverter. Here's our output terminals that are connected to the output terminals of our OutBack inverter. Here, parallel to this in this section here, is the protected loads panel. And feeding the inverter is our battery bank. And please note that the grid provides both the battery-less inverter and the OutBack inverter are both synchronized to the grid. So to the grid, they're still in a way listening to the grid. And if the grid fails, then the battery-less inverter realizes that, disconnects, and our inverter will then realize that as well and begin exporting power. And then once it starts exporting power, then the battery-less inverter notices that it has a nice stable 120 volt 60 hertz signal and allows energy to flow through it. So it's a very clever way to add backup to an existing system that didn't have, that wasn't designed to provide backup, that was just basically designed to inject energy into the grid. It's a very nice way to do it. So onto inverters and chargers. So our inverters, we have two main families of inverters. We have our smaller legacy FX inverters that a lot of people know about. And then we have our new Radian inverter that begins at 8 kVA. And our FX inverters range from 1.4 kVA up to 3.6 kVA. But essentially the function of the inverter is to invert from a DC source, like batteries, and it puts out a nice sine wave, a nice AC output. This is key because a lot of cheaper inverters don't put out a true sine wave. They put out either a square wave, a modified sine wave, and although they will work, these types of signals will work with some loads. For the more sensitive modern appliance type loads, they will not work. In fact, a lot of appliances are designed to accept a distortion, a voltage distortion, a signal distortion of no more than 5%, which these two signals here is both a square wave and a modified sine wave exceed. So I've seen people where they install a modified sine wave inverter, and it just doesn't work because the loads, the sensitive electronic loads, will simply not accept it. If you had a resistor or an incandescent bulb, it really doesn't care. But for the more sensitive loads, it does become an important. It becomes an issue. So here is our block diagram. So here we have the PV array feeding the charge controller, which is doing the charging of the batteries in a controlled manner. And here is our battery bank. The battery bank is, please note that the battery bank is essentially parallel between the output of the charge controller and the input of the inverter. In a very real way, if the batteries are fully charged, every single electron, let's say, that's being harvested from the PV array will go right through the charge controller onto the inverter and onto the grid if this happens to be a grid interactive system. It's only when the batteries are discharged that some of the current gets basically deviated into the battery bank. And the batteries, in that sense, are very, very smart because they basically will ask how much current they want from the system. So they are, in that sense, self-regulating. If they are basically fully charged and they're just floating, they require negligible amounts of current. It's in the milliamp range. Whereas if they are discharged, then they would require lots of current. But essentially, the system is designed so that the transfer of energy from the PV array to the grid or to the loads is very, very efficient. Here is an AC transfer, our AC transfer relay board, and this is the reason I have this here is because there's two things that are important to know here. Our inverters have essentially two types of currents. They have the AC input current, or what some people call the pass-through current, where the current essentially is passing through the inverter. And the best example of that is when the inverter is in a backup application where the inverter is basically a wire. We said in the previous slide that the inverter, unless something happens to the grid, the inverter allows the current to flow right through it. So that path, happens to be in this direction. So here are our input terminals: AC hot, AC neutral input. So when the grid is normal, switch 1 is closed, and the current flows from this node through the switch. From this node, it goes down and goes right onto our output terminal. And this here has an opacity for some of our models of 60 amps. For example, our VFX 3648, which is a 3.6 kVA model. This pass-through current is 60 amps, but the export current, meaning from the batteries or from the PV array, happens to be 30 amps. So if we divide 3600 by 120, we get 30 amps. And so there we have essentially two different types of current. We have the input current, or the transfer or pass-through current, and then the export current. And by the way, if the grid fails and the inverter realizes that it failed, it will basically open switch 1, close switch to and begin exporting from the batteries. And it'll just basically flow through this transformer, through the switch, and right onto the output terminals. And what I'm not showing here is that I'm just showing the power traces. I'm not showing the control and the monitoring traces because the inverter will continue to monitor the grid. So just wanted to make that clarification there. We have, in the case of backup, standalone, or off-grid inverters, we have essentially two models. We have a vented model, which is on the top, and a sealed model. And by sealed, I mean that I don't mean that it's a NEMA 3 or higher. They're both NEMA 1. But sealed basically means that it's the unit that you'd want to use if you were near the ocean or if you were dealing with a lot of insects, because our inverters are installed throughout the world. We needed a way to essentially make our inverters insect-proof and to help them deal with, we needed to help them deal with salt near the ocean and basically corrosive environments. And so that's the reason, that's where the sealed units came from, but both have to be installed indoors because they both have a NEMA rating of 1. The input voltages go from 12 volts to 48 volts. They both have the same function in terms of being able to work in a backup unit on the backup application. In addition to the 120 volt output, they also have a 12 volt 700 milliamp output that can be programmed to do things, to implement logic like start an automatic generator, for example, to start a fan, to a light, really any type of logic that you want based on voltages. And they're very easy to program, and in fact, they come with a lot of defaults. Although you would want to look at specifics so that the inverter can work in the specific application or installation. But if you just take one out of the box and you provide it the input and the input power, and it'll begin working. Perhaps not the way you'd want it to, but it'll begin working. These inverters, the off-grid inverters, can be wired to have up to 10 inverters in any system, and we'll get more into that. But basically, we can provide any type of single-phase system or three-phase system. Now, in a three-phase, we can only provide a three-phase Y system, not delta, and we provide a 12208 system. Now, for the grid interactive inverters, please remember that we talked about the voltage and the frequency windows that they are fixated to follow, that they're programmed to follow, and that's really the only difference here. They can accept pretty much the same. They can accept the same voltages from 12 volts to 48 volts. They also have a 12 volt 700 milliamp output. And they are both also, with the vented and sealed units, they're both also NEMA 1 rating. Now, these are not stackable up to 10. There are limitations, which we'll get into in a bit later. But the thing to note here, the important thing to note, is that if we wanted to use a grid interactive inverter in an off-grid situation, they would work. Now, where we would run into an issue is if someone had a generator, a low-quality generator, that didn't have the voltage regulation that these inverters are going to look for, that didn't have either the voltage or the frequency regulation, or if they had poor quality in terms of the power, in terms of the harmonic distortion and power factor. If that generator deviates from what these inverters are programmed to look for before they accept an AC source, then it's not going to work. And I've seen that happen too many times, unfortunately, where someone buys a grid interactive inverter only to find out that it's not going to play with their generator. By the way, all the grid interactive models begin with the letter G, So here we have GFX and GVFX. So this is a grid interactive vented FX inverter, and this is a sealed grid interactive inverter. Here are the combinations. So let's just first talk about off-grid, standalone, or backup type applications where we're not injecting energy into the grid. So here we have the first combination. We basically have a 120, 240 volt source, and here you can have 120 volt loads or 240 volt loads. And by 240 here, these inverters are 180 degrees out of phase, so it really is a 120, 240 volt, 3-wire or split phase system. And the limitation here is you can have up to 10 inverters. So here you could have up to 5 inverters feeding each phase. The parallel stacking is a little different. Here we have all 3 inverters feeding the same phase. So here we have basically we were paralleling all three inverters, and you could actually have up to 10 parallel inverters all feeding the same phase. The next stacking is essentially a combination of the 2 on top here, series and parallel, where you can have up to 5 inverters per phase for a total of 10. The XW240 here that we see, it's basically a transformer that allows us to balance the phases so that we're not going to overload the neutrals, and we'll talk more about that. And one of the things that I failed to mention initially is that this is part 1. We have 3 webinars, so part 2 and part 3 go into a little more detail. Essentially, part 3 we'll talk more about stacking and transformer functions and things like that. But for now, we'll just kind of stick to this topic here. The 3-phase stacking is the 12208 that we talked about, and you can power 120 volt loads or 3-phase loads from all 3 phases. Now, if you only had, let's say, if you had a single-phase load, but that used 3-phase voltages, for example, you might have a load that only requires 2 phases, but at 208, with a phase angle difference of 120, you can program our inverters to do just that, to provide a 3-phase source with only 2 phases, either phase A or phase B, C, or phase A and C. Now, the difference between an off-grid inverter and a grid interactive inverter is that the grid interactive inverters can really only be stacked in here or in 3-phase. So really the main difference is that, and we're going to be coming out with a new unit, a new hub that overcomes this issue, but for now, any system that is grid interactive can only have 1 inverter per phase. So we couldn't do parallel, and we couldn't do OutBack. And as an off-grid system, and I failed to mention this here, for off-grid systems, you can have up to 10 inverters. So you can have up to 3 inverters per phase, or one of the phases can have 4 inverters, and the other 2 phases can have 3 inverters. But essentially, for a grid interactive system, you can only have 1 inverter per phase. So that's kind of important to keep it. And we are going to be overcoming that issue pretty soon. This is the new Radian unit. This is, as I mentioned before, this is an 8 kVA unit with a 48 volt input only, 48 volt battery system only as an input. Now, unlike the FX inverters, where you need to buy a specific model for a standalone or off-grid applications, or a specific model for grid interactive applications, this inverter will actually do both applications. All you need to do is program it to say you're going to be in a grid interactive application or in a standalone application. Also, This inverter looks, it's an 8,000 watt inverter, and it really consumes very little compared to the output power that it can have. It only consumes 30 watts. It can take very high inrush currents. It can actually handle, although the continuous rated power is 8 kVA, the surge power is almost 17 kVA. It's 16.9 kVA. So it can handle loads like a starting motor, for example, that are known for having very high inrush currents, depending on the rotor design. So it'll handle these loads, those types of loads. And it's unlike the other smaller FX inverters that you can only have, you would have, if you had a 120-240 volt system, you needed to have 2 inverters. This inverter, the Radian inverter, provides a 120-208 3-wire system with the phases being 180 degrees out of phase. So it has it really is very useful in that sense because you don't need 2 inverters. It will do grid interactive or standalone applications, and it will also accept 2 AC inputs. So unlike the FX inverters, that if we have 2 AC sources like the grid or the generator, we needed to have a transfer switch. But here we don't. It'll actually take the grid and the generator, and so you basically have 2 AC sources. Because some of the special functions that it does are new, this inverter can only be programmed with the MATE 3, which we'll cover more, we'll go more into that as we progress. A big advantage with this inverter is that it's field upgradable. In the old days, if you had an FX inverter and you wanted to upgrade the firmware on the boards, on the control board or AC or power board, you needed to send that board in to us, and we would then upgrade the firmware and basically send it back to you. But now that can be done in the field because the MATE 3 have an SD card slot that allows you to just basically download the firmware from our website and upgrade the firmware in the field. Very, very big. It's a big advantage. So here is the voltage that the Radian is programmed to look for. So here we have a 120-240 volt source, and the phases have to be 180 degrees out of phase. So I've seen where people will have a 3-phase source, and they say, well, I'll just connect 2 of the phases. I'm providing 120-208. And I'll just program the inverter to accept the lower voltages, and so I should be okay. The issue with that is that the phases are going to be 120 degrees out of phase. They're not going to be 180, and so because the inverter is fixated around the 180 degrees, it's not going to accept the AC source. So very important that we qualify the source beforehand. The stacking or the paralleling of these inverters can really only be done in one direction. This is a 120-240 volt load and inverter, so we can really only stack in parallel. So here we have 3 8 kVA inverters in a 120-240 volt output type network for a total of 24 kVA at 120-240. Now, these can be stacked up to 10 also, so the limit here would be 80 kVA at 120-240, so it's pretty big system at that point. The hub, which is this center here, is essentially, it does the function of any hub. It provides the communications, and here we have 6 inverters and 4 charge controllers. We have 2 types of hubs. We have one that has 4 ports that we call the hub 4, and one that has 10 ports that we call, as you already guessed, the hub 10. So charge controllers. Charge controllers essentially do the charging in a controlled manner. So here we have our typical curve from our IV curve. Really what we do is we provide an ideal load to the modules. And so here's the behavior of a resistor. If you connect a resistor to the PV array, here's how an inductive load would behave. Here's how a battery load would behave, and here's an ideal load. So and this is exactly what we do, because our inverters because they track and look for the maximum power point, independent of how much sun there is. We basically provide an ideal load to that array. And so what that does is it will harvest more from the PV array than a conventional charge controller, and it's thrown around that the gain is roughly 30%, which basically means more charge current, more charging current for the batteries, and that's the advantage, that you would be able to charge your batteries, and thereby prolonging the life of your batteries, and of course the available energy that the batteries can give you. So here we see that the maximum power point tracking charge controller operates right at that maximum power point. So huge advantage over conventional charge controllers that are that don't react in that same way, that they're not looking for that maximum power point. They just see a source, they modulate, and then they try to charge the batteries as they go. The charge controller is essentially a DC-to-DC converter. So if we just work in terms of power and get away from voltage and current, we just think in terms of watts. If we have 1,000 watts coming in, and we use a nominal efficiency of 97.5, which basically means that we have 975 watts here, and if we happen to be charging at 59 volts, it basically means that our charging current will be 16.5 amps. And so the two things that we're kind of fixated on are that we have, in the case of the FM80, we have 80 amps of output charging current, and using a nominal efficiency of 97.5 basically means that at 12 volts we can have a PV array of up to 1,000 watts. At 24 volts, 24 volts meaning the battery bank, up to 2,000 watts, and a 48-volt battery bank, 4,000 watts, and a 60-volt battery bank, 5,000 watts. And so in part two, we are going to get into the sizing of these charge controllers, and we'll get more into the reasons why. But essentially, because we have this 80 amp limit and this nominal efficiency, it basically means that the higher the voltage, the more, the bigger the array can be. The FM charge controller is rated at 80 amps at 40C and has a maximum input voltage of 150, although at about 145 it'll start to get worried, and it'll start to basically step away. Now, these charge controllers also have a secondary output, 12-volt output, at 200 milliamps, and that can be used to implement, again, any type of logic, just like inverters. But it is only 200 milliamps, not 700 milliamps, like the FX inverters. The FM60 puts out 60 amps, whereas the FM80 puts out 80 amps. And from the electrical and functional standpoint, they are essentially the same thing, with the exception that the FM60 has a limitation of 60 amps for the output current. Here's a typical installation. So here we have our modules going through a combiner box, and then our combined currents go through the input breaker onto the charge controller, to an output breaker and onto the batteries. What this isn't showing, what this is not showing, is the GFDI breaker, which is essentially here at the output side. So here we have a GFDI breaker, and please note that we have 2 poles here. Now, on the output of the charge controller, we would have our 80 amp breaker, and then an additional mechanically interconnected 0.5 amp pole that is essentially what provides the ground fault protection. So on the line side of the breaker, we have connected the negative side of the system. So if we look over here, we have the negative of the PV array, negative of the charge controller, and the negative of the battery bank. So that gets connected to the line side. On the load side, we are basically connecting to ground. So if the current exceeds 0.5 amps, then it'll trip the breaker, and because they're mechanically interconnected, it'll also open the output breaker of the FM charge controller. Now, we said that these charge controllers have a limitation at 48 volts of 4,000 watts, but if you run into a system that's using a 48 volt and a larger array of, say, 8, 12, 16 kW, then at that point you would just simply parallel more charge controllers. They would all be charging the same battery bank, but would have independent PV arrays at their inputs. So here is, for example, if we had 2 charge controllers, we would essentially have a 3-pole GFDI breaker with 280 amp poles, 1 for each charge controller, and our 0.5. We also have a quad that it's a 5-pole breaker that has 4 80 amp poles. That's basically there. It can protect up to 4 charge controllers, and we still provide our ground fault protection. Now, once you get beyond 4, you can parallel more GFDI breakers, and UL allows you to continue doing that because the fault current, the permissible current, the fault current gets bigger in proportion to the PV array. So they allow up to 1 amp at 25K, up to 2 for 50K, and so on. Here is a typical installation with a GFDI. So here we have our negative terminal bus bar here with all the negatives from the system being connected, and the negative being also connected to the GFDI breaker, and then the output of the GFDI breaker just simply goes to ground. But it shows essentially the connections here. And if we have 2 charge controllers, all the connections would basically parallel. And we have diagrams and pictures of that in our manuals also. The temperature compensation is very, very important because the voltage response of batteries varies as a function of temperature. So if you were sitting at room temperature, you'd have a specific voltage response, but if it was, let's say, cold climate, and you were charging the battery, then that voltage response is going to be much, much higher. And the opposite happens in hot environments. The voltage response of the battery depresses, it gets a little lower. And so to adjust for that behavior, we have this remote temperature sensor that will basically take the batteries, will essentially listen to the battery's temperature and adjust the voltage parameters accordingly. So now on to batteries in renewable energy systems. In the world of batteries, and I'm only going to lead-acid batteries, there are 2 broad families that we can kind of group by application. There are non-cycling applications, and then there are cycling applications. And by a cycle, I mean a sequence of a discharge, followed by a charge. And a cycle can be either it can consume all the energy inside the battery, or it can consume 50% or 20% or 10%. And so the depth of discharge, as people would refer to it, if we had, as an example, a 100 amp hour battery, with amp hours being the energy units of batteries, if we had a 100 amp hour battery and we removed the entire 100 amp hours out of the battery, that is considered to be 100%. So the depth of discharge would be 100%. If we only removed 50 amp hours out of the 100 amp hour battery, that's considered to be 50% depth of discharge, or DOD. If we removed 25 amp hours out of a 100 amp hour battery, that's 25% DOD. So going back to our picture here we have a non-cycling application where these are essentially on float, trickle charged, and just ready to be used. And so in those applications, that's where the batteries might only be used once or twice a year, the batteries basically have to be built, designed, and chosen for being on float, for having very good float ratings. And in an application where the batteries are going to be used daily, like say an off-grid or standalone application, the batteries, the chosen batteries have to have very good cycle life. So here we have two very different applications and two different batteries that we would want to use. One on the one end, for a non-cycling application, we'd want to use a battery that can be on a trickle charge or a float charge for a long time, let's say 10 years, 12 years. And in a cycling application, we would want to use a battery or choose a battery that has very good cycling properties. Now, just a word of caution here. As you talk to customers, you realize that people will mean, well, it's just a battery backup, or it's just a backup application. But it's really important to qualify the application, because just because they mean backup doesn't mean that they're not going to use the batteries. In developing countries where the grids are not very stable, those grids might go out 2 or 3 times a day. And so the batteries will be used, discharged 2 or 3 times a day. And so if we use the battery that's designed for float applications, for very good floating applications, but not very good cycling applications, then we're going to misapply that technology into the application and have problems down the line. On the other hand, if we use the battery that is meant for a very high level of use in terms of cycles, everyday cycles, and we chose a battery that's designed for float, that again is going to lead to some problems. So it's very important that we apply the right technology here to the application. So the world of batteries can be broadly categorized into flooded, open, vented batteries, and into valve-regulated, typically called gel or HEM batteries. Either the gel or the HEM batteries, they're both VRLA batteries. They're not sealed batteries because they still produce gases and require some level of ventilation, but it's, the amount of gases that they produce are negligible compared to flooded batteries. And flooded batteries are called flooded because the components here are flooded with electrolyte. So in the world of flooded, you have basically that type of battery that we're all familiar with, which is the batteries in our cars. Then you have stationary backup batteries that have been used, for many decades in places like telecom. And then you have deep cycle applications, batteries that are meant to be discharged deeply and then recharged again many, many times. So the automotive batteries, they're not really designed for deep discharge, and they're designed to start the car, and that's it. A stationary backup battery, they're designed to be on float for many years. Some designs as much as 25 years on float. They're not really designed for a lot of cycles. And a deep cycle battery, as the name implies, is designed to be used daily. Now, in the case of the VRLA batteries, we have VRLA stands for valve-regulated lead-acid batteries. You have the gel batteries, and you have the AGM batteries. Now, there are differences between the two, but essentially, this technology has evolved over the years, and they've improved their life, their capacity, and just to note, just to cite one difference here, for example, in the case of an AGM battery, it has a float life of 12 years. The average AGM battery has a float life of 12 years, whereas a deep cycle battery is not going to last more than 3 years on float. Now, in the older days, AGM batteries didn't really have very good cycle life. They have maybe a third of the cycle life that a deep cycle battery has. But with today's designs, AGM batteries are now getting to the point where they can compete on cycle life, and they actually outperform floated batteries in float. They are maintenance-free. The VRLA batteries, both gel and AGM, do not require maintenance. And by maintenance, I mean the addition of water, whereas flooded batteries, they do require the addition of water. There is, of course, a cost that's associated with that. Gel and AGM batteries are more expensive. They can also be placed in applications where the ventilation isn't going to be very good, or where it's not either, but where the application is a combination of a siting application and a backup application. And a good example of that is systems where the batteries are going to be used one time per week, for example, where the batteries will see 52 cycles but throughout the year, but basically 6 days out of the week they're going to be on float. And so they do serve as dual-purpose backup / siting type batteries. And AGMs, they lend themselves very well for that. Gel batteries also. Gel batteries, they tend to do really well in hot climates. Gel batteries can handle low currents very well, but because of their construction and high resistance, they can't handle high currents as well as AGM batteries can handle them. AGM batteries can handle a huge range of currents, from low currents to very high discharge currents. Amp hour is the unit that it's really a unit of energy that you hear. And it's really just the product of the amps times the hours. So here you have, these tests are all 200 amp hours. So here we have a test for the discharge the batteries 2 amps, and the batteries ran for 100 hours. So 2 amps times 100 hours is our 200 amp hours. Here we have 50 hours for 200 amp hours, 8 amps for 25 hours, 20 amps for 10 hours, and 40 amps for 5 hours. And the thing that I'd like you to note here is that although they are all 200 amp hours, the running times decreased as we increase the current. And that's going to be the key when we're sizing batteries in part 2. And that's the reason battery manufacturers give us different ratings, the 5-hour rate, the 20-hour rate, the 100-hour rate. And we're going to be using those ratings to size the battery banks. Here is a picture of one of our energy cells. So here our 200 RE battery, for example, will deliver the 200 amp hours if we discharge it with 2 amps. So 2 amps, 2 times 100 gives us our 200 amp hours. If we came up to the, and this, by the way, these are hours, and these are in amp hours. So amp hours, hours. So if we went up to the 20-hour rate, we see that at the 20-hour rate, the battery gives us 178 amp hours. So if we divide the 178 by 20, so 178 divided by 20 will give us roughly 8.9 amps. If we go up to the 5-hour rate, which is 145.5 amp hours, it's 5 hours. It's going to be about 29 or so amps. So the thing that I want you to see here, the pattern to see is, again, coming back to this picture, that the higher the discharge current, essentially the less running time we're going to get. And so we're going to be using that to our advantage. Now, batteries are affected by, as we saw, the discharge currents or the discharge rates, but also by temperatures. And there are curves, specific curves that we have that any other battery manufacturer has, that essentially shows how that capacity gets affected. So essentially, the colder it is, the less capacity the batteries deliver. So, and that's going to be important once we start sizing batteries. Then we'll need to know how low that temperature is going to go, because if, for example, we have a 100 amp hour battery that will give us the 100 amp hours at 25C or at 77F, if our ambient temperature dropped from 77F down to, let's say, 40, we're going to get a very different capacity. And so we need to know, we need to take that into account as we're sizing the system and certainly sizing the battery bank, so that the batteries can serve the loads at the lowest expected temperature. Here is what a cycle life graph looks like, and this is the cycle life is for our 200 our energy cell 200 RE. So here, the thing to note here is that there is this dynamic relationship between the discharge, depth of discharge, or the DOD, and the cycle life. And so if we were to discharge the batteries, consume all the energy, we would get 425 cycles, discharge, recharge. If we consumed 80%, it'd be about 600 cycles, 50%, 1,800, and 10%, 6,200. So we can see here that at 10%, we get 6,200 cycles, but at 100% we get 425 cycles. So that's important to keep in mind as we are essentially trying to meet the expectations of the customer or determining what the life of the system is going to be. Batteries are essentially a perishable product. Although they don't have moving parts, they are affected by the way they are designed into the system. This is just a chart that shows compares big cycle batteries to dual-purpose batteries and automotive batteries. But the main thing to take away here is that if we use an automotive battery, for example, in an off-grid application, they're not going to last very long. I mean, we all know we all know that we're going to have to replace our batteries if we left our lights on in our cars, 2 or 3 times. The only reason I have this here is just to show that the system has to be both to serve the loads, but also to be able to charge the batteries correctly. Here we have the ideal life, what the ideal life would be for the batteries. If we overcharge the batteries, meaning we put in more than they actually need, we are going to reduce the life. If we severely overcharge the batteries, that's going to affect them as well. But if we undercharge the batteries, that is actually a lot more dangerous for them. They will die within months, and I've seen that happen too many times, unfortunately. So the system, at the end of the day, has to be able to recharge those batteries. So, and we'll talk more about that in part 2 of our webinar. This chart is essentially showing how temperature will affect the life of the batteries. The very famous electrochemistry equations basically says that the corrosion doubles every time the temperature increases by 10 degrees. So if a battery was going to give you a specific life at 25 C, at 35 C, that life is going to get cut in half. Now, as horrible as that might sound, this is where temperature compensation is very, very, very important. This is where it comes into hand because essentially we want to be able to charge the batteries properly, independent of temperature, and that's exactly what the RTS does, the remote temperature sensor. So it's not quite as bad if we have an RTS, but if we don't have an RTS, then the life is going to get reduced dramatically. Here's a table that essentially shows, it's a comparison table that compares AGM, gels, and flooded batteries by application. I'm not going to go too much into this, but just a thing to note here is also the self-discharge, which I haven't really talked about. Gel and AGM batteries, they will self-discharge a lot less than a flooded battery. For example, the nominal self-discharge of gel and AGM batteries is 3% per month, and this is independent of if you put them on wood or concrete or whatever material the batteries happen to be resting on. They self-discharge because of the chemicals they have inside, but they'll do that. So this is going to be, I'm going to leave this table here available for your review. That concludes the first part for webinar. We have 2 more parts. Part 2, we talk about the factors that we need to consider when we're sizing the components, like the inverter, the charge controller, the PV array, the battery. In part 3, we have essentially an example where we do we walk through a sizing exercise, and then we talk more. We go into a few more advanced topics with our products and a few of the key features that I didn't get into in part 1. So once again, my name is Ronald Paredes, and let me display the contact page here. So we will be posting this webinar on our website, and we'll be posting parts 2 and 3 also on our website. So thank you very much for taking the time to attend our webinar, and I hope you have a good day. Bye-bye.